This work in two modes. When the switch is on, inductors connected here to the supply, this diode will be off, current will follow from here through this part. So we have this circuit as you can see here. As you can see here, this is an on and this is an off. Okay, this is an on. When switch is off, current will follow through the diode and this part from here. So we have current following in this direction and current following in this direction. Now if I come to find the voltages of the two inductances and their currents, okay, now for the first inductance at on, this is on, okay, you can see the voltage here applied across the inductance. So we have VD. When it is off, the voltage here is the difference between VD and VC1. As you see, VC1 minus VO. Okay, sorry, here VD minus VC1. The same thing could be say for the second inductance here. When on, this inductance voltage is VO minus VC1, as you can see here, VC1 minus VO. And when we have off, which is here, this one, the voltage of inductance, this one will be in parallel with C and VO, so it will be minus VO. What about current? In on, current charge or energy store, and in off, release. By the way, the difference between this way and the previous way of discussion is I started from off to on, not from on to off. Now, after I explain the operation of the circuit and the waveforms, let me start. I copy here, paste it again, the waveform. I will start with finding formula to relate input to output voltage. First of all, VC1 is VD, VO in the on state of the, when we're talking about inductance number 1. So I can write formula. I will say, okay, VD by T on equal this voltage VD minus VC by T off. Rearrange, I got this formula. I come to inductance number 2. This voltage by D on, T on, and this voltage by T off. I arrange, I come up with another formula. See, VC1 equal VC1, so this element equal this element. I arrange them, I got the same formula for buck boost converter. Since we usually assume Pin equal P out, okay, I can use it to find the relationship between output to input current, which is the opposite, similar to the previous situation. Now, let's take example on Cook converter. He told me that Cook converter, its frequency is, by the way, before I continue with the example here, just to let you know that we assume usually the capacitor is a large, sufficiently large, and it would have constant voltage, and the current in the inductance is constant current. It means the current is increasing in this way, decreasing in this way, not in this way, decreasing in this way, no curve, just straight line. Okay. Now back to the example. He gave me L1, L2, they are equal 1 millihenry. Capacitor C1 is 5 microfarad. The output capacitor is sufficiently large, yield essential constant voltage. This is my assumption all the time. Now the input voltage is 10, the output voltage is 5, and it is supplying 5 watt. Oh, he told me the output voltage, power also. Calculate the percentage error in assuming constant voltage across the capacitor and constant current across the inductances. Now for the capacitor, we say it's the highest voltage in the circuit, which is input plus output, 15 volt. And I have formula D over 1 minus D equal output over input. I got duty cycle because I need duty cycle. Now let's come to delta IL1. Delta IL1 is, as you know, the voltage over L1 times off time. Okay? Now I have VC, VD, L, D, TS. I substituted, I got this current. Let's go to delta IL2. Also I have the formula output voltage over L2 times T off. I have all these values. Substitute, I got the same current. Since the current is the same, this means that the inductances are the same. Okay. And I can find the error. How? Have a look. This is the current 0.67 over delta IL1 over IL1, which is 0.5. I have it in the question. Then I multiply by 100%, it gives me 13.4%. This is how much the error in assuming delta IL1 constant. The same thing I did with delta IL2 over IL2, 0.67 times 100% over the current IL2, it gives me 6.7. This is the error. This is with respect to current. For voltage, let's see. Delta VC1 is 1 over C integration IL1, because IL1 follow in C1, okay, for off time. And IL1, I have it, 0.5. I just need to substitute here, duty cycle, okay, and here the capacitor, here IL, okay, then I got the voltage. Divide repellant voltage over voltage VC1, it seems to be there is some sort of error. So this is need to be considered in the real design. Now last converter, I finished buck boost and cook converter. Last one is the DC, is the full bridge DC converter, which may be used to control one of the application is DC motor. You know, this is DC motor, RA, LA, and back EMF. And you can see here we have leg A. This is leg A, contain two switches, TA positive, TA negative, which means that A positive connect to positive side, TA negative to the negative side. The same thing could be said for the other switch, TB positive, TB negative, okay, for leg B. Now the load is connected here to the center of, to the center here of leg A and to the center of leg B. One more issue need to be mentioned here. For each switch, we usually connect anti-parallel diode, D. It means in parallel but in opposite. I call it as example TDA, DA positive, DA negative, DB positive, DB negative. You may say, okay, why we connect these diodes? First of all, to protect the circuit, protect the switch, and to make a path for the current to follow through in situation the current reverse its direction. As example, energy stored in the inductance released, we can use it. Now let me talk about one of these legs, leg A as example. When TA positive, current will follow here, okay, so the voltage here is the voltage VD. So you see here VAN, between this is A, okay, as you can see here, the middle A, and this is N, the ground, then it's equal VD. When this one is positive, this one is 0, is off. When this one is on and TA positive is off, we have 0 current because this point connected directly to the negative. Okay. Now the difference between this point A and this point B will give me the output voltage. As you can see here, V output is VAN minus VBN. It's worth mentioning that the switch can be controlled using bipolar pulse width modulation, bipolar or unipolar. In bipolar technique, we switch off pair of switches. It means TA positive with TBB negative. Current follow from the positive to negative back here. Let me change the color. Okay. When I switch current TB positive, okay, TB positive follow through the switch and return back here, then I have the voltage across the. Now last issue is if I compare the output power with respect to the switch power in term with respect to the x-axis, the D, I can see the step up is a straight line, the step down is straight line, and the pulse here represent the buck boost and the Cook converter, while here is the full bridge. What can I come up from this figure? I come up that there is variety of control, good control for buck boost, Cook converter, and full bridge, okay, but limitation in the output power. From the other side, better output power, I can go up to 100% for step down and step up, but the variety in control is limited. I will stop here.